So I defined the ring of symmetric functions. So I'm following pretty much word for word McDonald's university lecture series. Uh, it's a small booklet called Symmetric Functions and Orthogonal Polynomials, and we're just doing the first chapter. The ring of symmetric functions was introduced as it's not quite a polynomial ring. There are infinitely many variables, so to speak. And then the various bases which are indexed by partitions. And the most important way of organizing partitions that we'll be using here is the dominance order. And here's the dominance Hasse diagram of dominance order for partitions of 6. And then we use Young diagrams to visualize partitions. There's the notion of the conjugate of a partition. The simplest, most obvious basis of symmetric functions is the basis of monomial symmetric functions, where you fix a partition lambda and you just sum over all monomials which are permutations of which are obtained by permuting the monomial x1 to the lambda 1, x2 to the lambda 2 by permuting the variables in that monomial. And that gives you the monomial basis. Then there's the basis of elementary symmetric functions, which are which have all monomials with ER is the sum of all monomials with R distinct variables. And then there's the complete symmetric functions, where now you allow all monomials of degree R. And then there's this nice relationship between the complete and elementary symmetric functions, summation HR En minus R with the sign minus 1 raised to R is 0. For n greater than or equal to 1, obviously for n equal to 0, you just get H0 E0 is equal to 1. We will be using that in today's lecture. And then another very important feature of symmetric functions is this involution called omega, which takes ER to HR. And then we have another basis called the power sum symmetric functions, which are just the rth power sum symmetric function is just summation xi to the r. And we studied the relationship between the generating function for power sum symmetric functions and complete and also elementary symmetric functions. Okay. And finally, we defined scalar product. So for this, I'm using this product, which is called pi of x comma y. And this is, we will be looking more closely at this. And we're also using this device. So this, where does this live? This is a symmetric function in two sets of variables. So another way of thinking about this is that you can think of symmetric functions as, so let me just make this clear because it could be slightly confusing. So pi xy is a symmetric function in two sets of variables. So in some sense, you can think of it as symmetric functions in the variable x, and then you take symmetric functions in the variable y with coefficients in symmetric functions in the variable x. Or you can think of it the other way around, or you can think of it as so we'll call this ring wedge xy just for now. So this means symmetric functions in the sets of variables x and y. And we are working mostly over integer coefficients, but sometimes we need rational coefficients like power sum symmetric functions. The change of bases involved rational numbers when you look at other symmetric functions. So the other thing, you can think of this as wedge x tensor lambda x tensor lambda y. So it's a tensor product of these two rings. And this is, I guess, a tensor product over the field K that we are working on, or the ring. What was the, yeah. Anyway, so that's where we are working with these products, infinite products, Where does it go? Yeah, this pi of xy. So here it's an infinite product in two sets of variables. Okay, so now let's get to today's lecture proper. So this is lecture 2. Anyway, any questions about the earlier stuff? Maybe this is a good time to ask. Also, I should thank Arun Ram for the wonderful exercises he sent on lecture 1. Okay, so I assume that that means there are no questions. Am I audible? Actually, I'm not getting any feedback.
Yes, you are.
Okay. Somehow, sometimes when you're on Zoom, you feel like you're talking to the void. So
Yes.
theorem. So the thing is, we've already seen a couple of expressions for this pi xy. One was that pi xy is summation p lambda x p lambda y sum over with the weights 1 over z lambda. The other was that pi xy is summation over lambda m lambda hy. And we actually defined a scalar product on symmetric functions by saying that these two bases, h lambda and m lambda, are dual bases. So it's a scalar product with respect to which these are dual bases. And now I'm going to show that whenever you have, so what I had promised last time, so if you have bases u lambda and v lambda of symmetric functions, and now we'll just work over Q, indexed by partitions. Of n. So this is degree n homogeneous symmetric functions with rational coefficients. Then saying that this inner product u lambda v mu, they are dual bases with respect to this inner product is the same as and the second condition is this condition u lambda x v lambda y equals pi of xy. So these two conditions are equivalent. So whenever we see an expression of this kind, we know that we found a pair of dual bases of symmetric functions. And so here, for example, this was how we defined the inner product. But here this will say that the inner product of p lambda with itself is z lambda, and the inner product of p lambda with p mu is 0, because of this condition. It says that p lambda is the dual of the basis 1 over z lambda p lambda. Okay, so that's that. So let's give a proof of this.
Sorry, so here both, so in the first statement you also have for all n, and in the second statement you're summing over for all n.
Yeah, for a fixed n, for all n, yeah, I guess lambda partition of n, this should be for all n, and this should be, yeah, this is as it is, yeah.
Right.
Yeah, thanks, very good point. So so now yeah, the proof is kind of well, you just try to expand these things in terms of, so we defined an inner product in terms of h and m, so let's just expand u in terms of h. And so this is a lambda rho, h rho, let's say for some coefficients a lambda rho, and v mu, let this be b mu sigma m sigma, right? So, and now let's just evaluate the inner product. So then what do we get? We get u lambda v mu is equal to summation over rho. Okay, and then uh, uh, let's see. So yeah, so what we know is h rho and m sigma are dual bases. So what we'll get is summation over rho a lambda rho b mu rho. Actually, we'd have summation over mu rho and sigma a lambda rho b mu sigma, but now but that times the inner product of h rho and m sigma, but the only terms that survive are when m is equal rho is equal to sigma, and so we get this. So the first condition, so let's call these conditions something. So this is the condition 1, and this is the condition 2. So the condition 1 is equivalent to saying that summation over rho a lambda rho b mu rho is delta lambda mu. Okay, now what about condition 2? So let's look at this sum. So we look at summation u lambda x b lambda y, then this is going to be, well, so sum over all lambda. And let's, so this is equal to sum over lambda, sum over rho. I need to expand both these things. A lambda rho, h rho x, b lambda sigma, m sigma y. Okay, and now let's just collect the coefficients of, so of this h rho x m sigma y will have coefficient sum over lambda. So
Rho and
this is sum
sigma
over rho and sigma here.
upstairs as
And,
well.
yeah, and then the coefficient of this will be sum over lambda a lambda rho b lambda sigma. Now for this to equal, we want this to be equal to summation h lambda, or let's say h rho x m rho y. Okay, so we want this expression to be equal to this expression. Now the point is that all this is happening inside this ring lambda x tensor lambda y, and these are sort of pure tensors. This is h rho x tensor m sigma y in that ring. So, and these are bases. So what we want is that all these coefficients should match with the coefficients here, which means that we must have, uh, and this is a necessary and sufficient condition, that these coefficients should be 1 if and only if sigma equals 1. So this thing is equivalent to the condition 2. Okay, so I hope that's clear. So condition 2 is saying that this is equal to this, and that turns out to be the same as this condition, because these things form a basis of lambda tensor, lambda x tensor lambda y. So now the second condition has become this. So now all we need to show is that this condition over here is equivalent to this condition here, is equivalent to this condition here. Okay, but now they look very similar, but they're not exactly the same, right? So if you think about it, this condition, if we take, if we think of A and B as forming matrices whose rows and columns are indexed by partitions, then this is saying that A, B prime, is the identity, and this one is saying that A prime B is the identity, where prime stands for transpose. Okay, but AB prime is the identity is equivalent to A prime B is the identity for any two matrices. So these indeed are equivalent. So these two conditions in red boxes are in fact equivalent. So let's call this 1 star, 1 prime and 2 prime, 1 prime and 2 prime. Since 1 prime and 2 prime are equivalent, 1 and 2 are also equivalent. So we can read off dual bases from this condition here. Okay, so that completes the proof, and now an immediate corollary is that P lambda P mu is Z lambda delta lambda mu, as I said, because P lambda and 1 over Z lambda P lambda are dual bases. And so from this you can conclude that so we have an almost orthonormal basis, we have an orthogonal basis, and this from this we can conclude that this inner product is symmetric, and on each graded piece which is finite dimensional, it is positive definite. And one more nice fact is that which we haven't proved so far is that the power sum symmetric functions form or maybe we showed that they form a basis, yeah, but now they form an orthogonal basis. So they form an orthogonal basis of lambda n over q. So and also finally omega pn is equal to omega p lambda is equal to we saw this last time, it's plus or minus p lambda for all lambda. So this implies that omega is an isometric. So this lemma nicely ties up the properties of this inner product that we have introduced with all the things that we have looked at earlier. Okay, so now we are ready to introduce the most important basis of symmetric functions, namely the Schur functions. Okay, so we'll do it using Cauchy's bialternant formula, and it comes as follows. So you take alpha to be any integer vector, that means a vector with non-negative integer coefficients, and define A alpha to be a determinant. It's the determinant of the matrix xi to the power alpha j, and this is an n by n matrix. Okay, so this is now a polynomial in the variables x1, x2, xn. And explicitly, when you expand this determinant, this is summation w in Sn epsilon w x to the power w alpha, where I'm using this notation x1 to the power whatever index there as well. Maybe I should say w dot alpha. Okay. And clearly, this is going to be an alternating polynomial. If you interchange any two variables, it changes its sign. And another point that you notice is, so A alpha is alternating. And the second fact is that A alpha equals 0 if any two components any two components of alpha are equal. So this thing vanishes unless all the components are equal. And in any case, you know that no alternating polynomial can have monomials where two of the powers are equal. And here's an exercise for the tutorial. Uh, so firstly, yeah, so the degree of A alpha will be the sum of these alpha 1 up to alpha n. So exercise is that you show that take all, so A alpha where alpha runs over all strictly decreasing vectors of this form. And alpha, the total sum is n. This is a basis of the set of alternating homogeneous polynomials of degree n. Okay, so that's an exercise. A very special case of this A alpha is the Vandermonde determinant. So if you take delta to be the vector n minus 1, n minus 2 down to 0, then A delta is just the determinant of the matrix x1 to the power n minus 1, x1 to the power n minus 2 down to 1, x2 to the power. And this matrix we know is the famous Vandermonde matrix, and its determinant is given by xi minus x. Now let me just remind you how we prove this determinant identity. So the usual, well, one of the ways of proving it is to first note that since this the determinant is changes sign upon interchange of xi and xj, it must be divisible by xi minus xj for all I not equal to j. And so the left hand side here in this identity is divisible by the right hand side. But then the degree of both these things is the same. And so the left hand side divided by the right hand side has to be a constant. And you can find out what the constant is by looking for the coefficient of some monomial. And usually we pick the monomial x1 to the n minus 1, x2 to the n minus 2, the monomial that comes by multiplying the diagonal entries of this matrix. So that's the proof of that. And we will be using this technique later to also compute the Cauchy determinant, which we will need. Okay, so now we saw that this determinant vanishes when two components of alpha are equal. One way to make sure that no two parts of a vector are equal is to consider uh, alpha equals lambda plus delta, where lambda is already a partition, it's weakly decreasing. But we don't need to take so let's just define this. So if we take this where lambda is a partition, then uh, this is non-zero. Lambda plus delta has distinct parts because lambda is already weakly decreasing and we're adding to it this vector which is strictly decreasing. The sum will be strictly decreasing. And so A lambda plus delta is non-zero. And we have, again, since it's alternating, it's divisible by A delta. And Cauchy defined the Schur function in n variables as a lambda plus delta for a delta for every partition lambda with at most n parts. Okay, so at most n non-zero parts. So we could write, yeah, we could just write it like this. Some of these parts could be zero. Okay, and the other thing is, suppose you take S lambda, and this is very easy to see. If you take S lambda in n plus 1 variables, and then you take setting x n plus 1 to be 0 gives um, S lambda x1 xn. What happens is that in the determinant, you, you lose the last row, and yeah, well, I mean, so mostly it becomes a block thing. So, okay, so I'll leave that also for you to check. And so, so what we get is taking limit as n tends to infinity. Letting n go to infinity in the usual way gives S lambda symmetric function. Okay, and this is called the Schur function corresponding to lambda. So that's the Cauchy's definition of the Schur function, and using this using this using this first exercise, you can actually show that so any alternating polynomial is divisible by a delta. And so using this, you can show that multiplying by a delta gives an isomorphism from symmetric polynomials of some degree to alternating polynomials of that degree plus the degree of a delta, which is n choose 2. And using that, you can show that these Schur functions actually must form a basis of symmetric functions. And that's how, you know, one traditionally shows that Schur functions form a basis. Okay, but we'll use a slightly different approach here because it is going to be important in how we define other bases like Hall-Littlewood's symmetric functions and McDonald polynomials.
Sorry, Amri, could you scroll up for just a minute?
Yeah, sure.
So this n goes to infinity part.
So what I'm saying is it has the stability property.
The project, the limit of the finite.
Yeah. So it defines an element of the projective.
Right. Okay. Thanks so much.
Okay. So here's another way to show that these S lambdas form a basis. So let lambda be a partition of n. Then S lambda is m lambda. Okay, one more thing I should mention before I go on, that this S lambda makes sense even if lambda is not a partition. This now just defined as a lambda plus delta over a delta. There are two possibilities here. One is that if lambda is a partition, we know that a lambda plus delta definitely has distinct parts. But if lambda is not in weakly decreasing order, then it's quite possible that a lambda plus delta is has two parts of a lambda plus delta coincide. And so then this could be 0. So could be 0, or it could be plus or minus a Schur function, or there exists partition mu, another partition mu, because it would just be this a lambda plus delta. If lambda plus delta has distinct parts, then you can arrange them in strictly decreasing order again, and that would correspond to rearranging the rows of the determinant, and so you would get uh, another partition mu. So after you rearrange the rows, you subtract delta, you get a partition mu, and then this s lambda is plus or minus s mu. Okay, so we will use this more general notion, but we call it a Schur function only when lambda is a partition, i.e., it is weakly decreasing. Okay, and here's the theorem that S lambda is M lambda plus mu strictly less than lambda, and this is in the dominance order, K lambda mu M mu. So this is a kind of triangular um, uh, change of so when we're saying that when we go from M lambda to S lambda, the change of the expansions form a triangular matrix, and this will imply that the Schur functions also form a basis for symmetric functions. Here the only symmetric functions are all of degree n. So because when we say mu less than lambda, we insist that mu has the same size as lambda. And here we'll only prove that these are rational, but they turn out to be integer. So the proof for this, we'll work with n variables where n is greater than or equal to lambda. And if we show it for every such n, then we are done. N is greater than or equal to the size of lambda. And so what we have is, what is m lambda times a delta? Well, m lambda is summation over mu in the Sn orbit of, so we are working with n variables, even though I'm writing them as if they are just symmetric functions. But lambda is padded with enough zeros so that it becomes a vector of length n. So then Sn dot lambda makes sense. And then we also have, so then we are expanding this determinants, we get W belongs to Sn. And so this is, well, maybe this is just x to the mu, and this is epsilon W x raised to W dot delta. And so I can write this as a double sum. And for good measure, I'll also interchange the, does this make sense? Let me write it down and then see if it makes sense. X to the power, um, so what I get is mu plus W lambda, but since mu is running over an entire Sn orbit, I can put that W into that. So I get W times mu, W dot mu plus delta, not lambda. Okay, so is this okay? But this is nothing but um, this is nothing but sum over mu. Why did I do that? Mu in Sn lambda, W in Sn. This is nothing but sum of mu in Sn lambda, A mu plus delta. So now these are yeah. So what this means is that m lambda is equal to sum over mu in Sn dot lambda of S mu, where these are not just the Schur functions, but the more general things, because these mu's are not necessarily partitions. So now to make this, so it's, we are not quite there in terms of expanding m lambda in terms of Schur functions, but what we will, we need to take care of these, there are these different things which are not even permutations. So so here's the fact, claim, if mu is a permutation of lambda, and mu is not equal to lambda. So we're taking the parts of lambda and permuting them, and we get something that's different from lambda. Then either S mu equals 0 or S mu is equal to plus or minus S nu. It has to be, I mean, we always had this dichotomy. This is either 0 or it's a this thing, but now I'll add the point that where nu is strictly less than lambda. And why is that? So proof of claim is that uh, if 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 mu is w dot lambda, uh, w dot lambda,
Sorry.
yeah,
In this claim, is lambda somehow a partition or something?
in this claim, yeah, lambda is a partition. Yeah. So here we are looking at, yeah. So yeah, it says so. Sorry. This
Okay,
is okay,
lambda is
but
that
it's not
lambda.
clear because yeah. So I should say let n be a partition. Let lambda be a partition.
And just because you're appealing to something that you stated before this theorem where you declared lambda.
No. In fact, I never said it for here. So this is an independent statement of this. So I need lambda to be a partition here. But m lambda as such, we said that we would take lambda to be a partition, though it makes perfect sense for any.
I just meant for
Yeah.
the thanks.
So lambda has to be a partition here, and that's the yeah. So mu, suppose mu is w times lambda, then then what we want is, so we are looking at some partition. So we're looking at mu plus delta, right? So mu plus delta. So mu plus delta is going to be uh, suppose if mu plus delta is going to be nu plus lambda delta for some partition mu. That's when we have S mu is plus or minus S nu. It will be the sign of this, maybe not for some partition nu, for some new partition of n and w in Sn. Then what we have is nu is equal to u dot mu plus u delta minus delta, right? U delta minus delta. And so now we have, of course, that nu is a partition, and u mu is again going to be a permutation of lambda. So u mu is less than or equal to lambda. U mu is less than or equal to lambda, because lambda was in weakly decreasing order and then we permuted it, so we can only make it go down. And also u delta minus delta is strictly less than 0 because its delta was strictly increasing if u is not equal to the identity. So what we get is nu is less than lambda if I should say if w is not equal to the identity. So nu is strictly less than lambda if w is not equal to the identity. And so that means that m lambda is, so now we go back to this expansion here. So this is saying that m lambda is, of course, there's s lambda and then there's things coming from nu strictly less than lambda, a lambda nu s nu. And these are actually, yeah. So inverting this gives, so this is again a triangular relationship with ones along the diagonal. Gives the statement of the theorem. I suppose this actually shows that these a lambda nus are integers, and therefore the k lambda nus are also integers, not just rational numbers. But what it doesn't show is that these are non-negative. So it turns out that these k lambda nus lambda mu's are non-negative, and they are what are called Koska numbers, which we will see some point later in this workshop. Okay, so corollary is that S lambda lambda r is a basis. Okay, now now the what is so special about this basis of Schur functions, and it is S lambda x S lambda y is product x. What this means is that this basis is a self-dual basis. In other words, it's an orthonormal basis. And there are many ways to prove this. I'm following McDonald. I'm going to do it using the Cauchy determinant, which is very interesting in its own right. So firstly, we will look at this. So this is maybe a theorem or whatever. It's a very famous determinant. Uh, xi plus yj is equal to a delta x. So this is the van der Waals in the variables x. So maybe I should be a little careful here. I can't really do this with infinitely many variables. So let's fix some n and take n variables of kind type x and n variables of type y. So this is a determinant of an n by n matrix, and this will be again in x1, x2, xn, and a delta y divided by product, uh, and then again I have to take ij going from 1 to n, xi plus y. So this is called the Cauchy determinant. Now let's look at this. So proof of maybe I'll proof of Cauchy determinant formula is here's a nice exercise. Evaluate determinant 1 over 1 plus ij, 1 less than equal to I less than equal to 1 less than equal to ij less than. So this is, if you look at Kratenthaler's article on determinant evaluation, this is one of the first examples it gives. So this determinant is very difficult to evaluate when you just look at it like this. But once you make these things variables, then it becomes a Cauchy determinant. And the idea of the proof of this Cauchy determinant formula is very much like what we did when we proved that the van der Waals determinant is product of xi minus xj. So you just we'll pull this over to the other side. We'll show that that product is divisible by a delta x and a delta y. The degrees are going to be the same, and so we just need to evaluate one coefficient, and that coefficient will be 1, proving equality. So so note that determinant 1 over xi plus yj. If you don't mind, I'll just skip these things saying I less than ij between 1 and n. I'll also skip the index of multiplication xi plus yj. So if you look at this, if I were to interchange, so this thing is symmetric in the variables xi and the variables xj, but this thing is skew symmetric or anti-symmetric in each of the variables. Uh, in both sets of variables x and y. Okay, this guy is not a polynomial, but once I multiply by this, then I can, I can take the first row and multiply it by x1 plus y1, x1 plus y2, x1 plus y3. So I can fix an I, take all the terms which involve x1 and multiply the first row by that. I can take all the terms that involve x2 and multiply the second row by that. And then this product actually becomes a polynomial. Is an antisymmetric polynomial. And what is the degree then? The degree becomes so mm, so this thing has degree this thing has degree I guess n squared, and this thing has degree, so to speak, minus n. So this is of degree n squared minus. Okay, so it's antisymmetric and it's a polynomial and it's of degree n squared minus n. And this so since it's antisymmetric polynomial, it's divisible by a delta x, a delta y, and moreover the quotient is a constant, is of degree 0, because a delta x, remember, it's of degree 1 plus 2 plus dot 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 up to n minus 1, which is n choose 2, which is n squared minus n by 2. So n so you add so that's the degree in x is the degree in y, and so the whole thing, all these variables homogeneous of degree n squared minus n. So this is a constant. So we need to check that the constant is 1. Uh, so here's an exercise again for your tutorial. Coefficient of x to the delta, y to the delta in uh, this expression xi plus yi, determinant of 1 over xi plus yj is 1. And of course, coefficient of x to the delta y delta in this a delta x, a delta y is also 1, because the coefficient of that in a delta x is, so that's easy. In this and a delta x, a delta y is 1. So they differ up to constant, and then one of the coefficients matches, so they must be equal. So that's the proof of the Cauchy determinant. So now from Cauchy determinant to this identity on Schur functions, how do we do that? So we've evaluated the Cauchy determinant, and now let's get back to this. So now replace xi by minus xi inverse in the Cauchy determinant. So what you'll get is minus xi inverse plus yj. But then you multiply that by xi and you'll get minus 1 plus xi yj. Maybe you multiply it by minus xi and you'll get 1 minus xi yj. So you need to work this out a little carefully, but make sure that the signs and all the things you multiply work out. But if you get, what you will get is determinant of, so let me just say this again. So you're getting 1 over minus xi inverse plus yj, which is um, so if I multiply the numerator and denominator by minus xi inverse, I get minus xi inverse over 1 equal 1 minus xi.
By minus xi.
Yeah, so
not xi inverse.
I get 1 minus xi. And on the right hand side also, I will be doing similar things, but here I would get xi inverses, and then you have to check that everything sort of uh, works out. So what you get is 1 over 1 minus xi, yj, and still you will have here a delta x, a delta y, and but then you will have, instead of this product of xi plus yj, you will have this. Remember this pi xy, what was it? This pi xy was product of 1 over 1 minus xi yj. So what we'll get here is that. Pi xy. Okay, and all this is in n variables. Now look at this thing. So the usual trick we do is we take, whenever we see 1 over 1 minus something, we write it as an infinite geometric series. So this is determinant of summation uh, um, x I to the a y j to the a. So maybe this yeah, greater than or equal to 0. This matrix. And if you write this, if you expand this determinant, then you get summation w in Sn, sine of w times product over I, just expanding the determinant. And what you get is summation, let's say ai greater than or equal to 0, xwi to the power ai, y. I'm commuting the I indices into the j indices as we usually do. Yeah. Okay, and if you think about what that is, well, that's just sum over alpha running over all multi indices. That is alpha in z greater than or equal to 0 to the power n a alpha. That's what this part gives. And then we have y to the power alpha. But that is nothing but, so if you look at the terms that survive, and you'll get all permutations of distinct uh, 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 partitions here, and these signs will also keep swapping as those things change. And so what you get is actually just sum over lambda, a lambda plus delta in the x variables, a, this is in the x variables, a lambda plus delta in the y variables. Okay, so that's the and that basically proves it, right? Because so what we get is this determinant is a lambda. Yeah, so exactly. So now dividing by a delta x, a delta y, you get uh, uh, dividing by a, this identity by a delta x, a delta y gives the identity for true polynomials. In n variables for every n, and hence also you get it for yeah, no, that's all I would say. In n variables for every n. Yeah, and so then taking limit uh, as n goes to infinity gives uh, the identity for all n. So so this shows that these Schur polynomials actually form an orthonormal basis for symmetric functions under the inner product, which is often called the Hall inner product, under the Hall inner product. So what we have is that, and this is very important, that Schur functions are given by this. They have an upper triangular change of basis with respect to monomial symmetric functions. And so if you take these Schur functions, if you take the basis, start with the basis of monomial Schur symmetric functions and write it in some order which is a linear extension of the dominance order, then you apply Gram-Schmidt process, then you will get a basis which has these properties. right? But actually what we have is, so these two would be enough to determine Schur functions uniquely. But actually we've proved something more. We have S lambda S mu equals delta lambda mu for all lambda and mu, not just when this inequality is satisfied. So what this means is that this is over determined. Okay, so these extra identities come are uh, are coming for free, and it's not at all clear that if we started a priori, it would not at all be clear if we just started with m lambda, we had some inner product on our space, and we applied the Gram-Schmidt process, that these inequalities would follow. And so in some sense, so this is going to be a recurring theme when we study these generalizations of Schur functions. They will be determined by uh, they will be determined they will be over determined by a triangularity condition and an inner product condition, and so you always have to prove existence. Okay, so that's what we're going to see again and again when we look at different families of polynomials. So I'll stop now, except I'll take a couple of minutes for those of you who want to really. Oh, there's comments here. Uh, I should think of pi. I don't remember what this was about. Pi as formal power series in xi and yj. Yeah. But Arvind, this is when you're talking about the two variables, but they are also symmetric in the two sets of variables.
Yeah, but
Yeah.
he wants to.
No, I did not actually. So that you said something about lambda x y. Uh,
Yeah.
so I think the
Oh,
infinite sums are there. That is what I am saying. Like,
oh, because I didn't put any parameter which closes up the thing, right? Yeah. So yeah, we will be looking at infinite sums. So maybe I should be talking about lambda hat instead of lambda.
No,
yeah,
it's
yeah.
not
So
necessary. I mean, we think of this as formal power series in these variables.
yeah, but the way I defined lambda, we didn't allow formal power.
No, we don't allow formal power series. But this pi as an object is a formal power series in these variables, and uh, when you expand them, you're looking at any coefficient of any monomial, right? So, I mean,
That's true. That's true. When you have an identity like this, uh, no, but the question is, where does this live? Where does this expansion live?
I mean,
So
this
you're
In the
saying
formal power
formal
series.
power
Yeah, I
series.
see. Yeah, that's true. But I said it lives in lambda tensor lambda, which is not quite that.
No. The objects. I mean, the things that you expand in live there,
Right. But the whole thing doesn't live there.
but the sun doesn't.
Okay, and I just want to take a couple of minutes to tell you how to compute with. This was something that Arvind said he will also do in his course. So I just want to show you quickly how to compute with uh, symmetric functions in sales. So so let me just uh, start up that. Oops, my browser crashed. One second. Uh, okay. So sorry about that. So yeah, so you should try this out. If you don't have a Sage installed on your computer, you can go to the website cocalc.com and fool around there. But certainly, if anybody wants to prove theorems about symmetric functions, it's very helpful to have these tools. So the ring of symmetric functions in Sage is constructed by a simple command like this: R equals symmetric functions, and you can specify the ring over which you want to work. So I've just taken QQ, but you can also, which means rationals, you could take ZZ, which is integers. And the different bases are just constructed as follows. You have the monomial bases, complete bases, elementary bases. Oops, what is this R? That's no R. I'm using the same notation as I used in the lecture. Power sum and shoot. So how does this work? So you can construct a symmetric function in one of these bases. So I want to construct the Schur function corresponding to the partition 2, 1. I just type S21. Okay, that doesn't seem very helpful. But let's just I can also pass a partition instead of the part, writing it like this. This is useful when you're coding. But I can check, for example, if the Schur function corresponding to the partition 5 is the same as the Schur function, is the same as the complete symmetric function corresponding to 5, and that gives that works out as true. So I need to run all these things from the PV. So let's. Okay, so S5 turns out to be S11. H5 S111 turns out to be E3, and so you can do that. Now, but what we may be more interested in is going from, say, a power sum symmetric function to a complete symmetric function or something like that. So let's look at S21. That's a Schur function. I want to know how to expand it in monomial symmetric functions. That's one of the theorems that we proved today, that you can expand Schur functions in terms of monomial symmetric functions and have this triangularity property. So what you do is you take this object which is S21, that's the Schur function, and you push it into the symmetric functions with monomial basis. So the way you do that is you just take M and you say M and this thing. So this is like pushing something in the Schur basis into the monomial basis, and then Sage will expand it in terms of the monomial basis. The other thing is you can ask for a particular coefficient. So I can ask for the coefficient of the partition 111 in this Schur function, and it gives me this 2. I'll share this worksheet with you later so that you can play with it. Here, for example, I have constructed, using this technique I've shown you, I've constructed the base matrix for expanding complete symmetric functions in terms of monomial symmetric functions. And it has this very nice matrix. Here is another example where I try to compute complete symmetric function in terms of the power sum basis, and I get these very nice numbers in the denominators. These are you should recognize them as the Z lambdas, where lambdas are the partitions. So we've seen this also, that if you take a complete symmetric function, then it's a sum of power sum symmetric functions with these denominators Z lambdas. So you can verify that here. This way maybe we'll talk about next time. Jacobi determinant. I was hoping to do it today, but Jacobi 2D determinants and so on. But I'll share this with Venkatesh, and those of you who are interested in computing with Sage should play with this a little bit and familiarize yourself. So I'll stop with that. Anyway. Sorry for going over time. You can ask questions.
Hello, sir.
Yes, Vigendra.
Yeah, so can we identify somehow in variable x, y and get like polynomial form, that symmetric function in Sage?
Yeah, you can do that. Let me see. I have done it. Let me just see if I can do it right now. Yeah, that's of course, if you expand in monomial symmetric functions, you can write it down. But
you can write it down like.
Yeah. So I think we can do P32 dot let's see, there's a method. Yeah, there's a method called expand, and I can expand it in 4 variables. There you go.
Okay.
So you can choose the number of variables as well. So the variables are x0, x1, x2, and so on.
So just I have to call this expand function.
Yeah.
Okay, thank you.
Though in practice, I rarely find myself doing this expand. These are much easier to work with. This base changing basis.
Okay, sir. Thank you.
I have a related question. So when you expand it in terms of polynomial, can you multiply a symmetric function by a polynomial in that way? So does it?
So for that, you need to take your polynomial and convert it to a symmetric function, right? Or you can convert both of them to, okay, so you want to get it back in the symmetric function ring, right?
No, multiply a symmetric function by a polynomial that's not necessarily symmetric. So that can you do?
Well, that's fine. So you just take convert it to a polynomial, like I showed Mrigendra, and then you multiply it. What's there?
Is both belong to the same class, then says
You'll have to make sure they belong to the same class. So that may require a little bit of. So what is the class? So what we can do is we can get the class. Huh? So let's call this expansion. And so what we'll do is we'll say R equals iska baap, so to speak. Yeah. So now R is yeah, there you go. And now you can just say so here's a little trick I use. X equals dict. So you want to get the variables, okay? So if you take R dot gen, that will give you the variables. Okay, so you can put them in a dictionary. You can say X equals dict enumerate R dot gens. And now x1 will be the variable x1, x2 will be the variable x2. And so now I can take x1 into expansion, for example, and get my non-symmetric polynomial. Oops, x, I have to say x1. It's a dictionary. Okay, so now I have got this non-symmetric polynomial, which is a product of the evaluation of that symmetric polynomial by x1. I'll share this thing. So yeah, this is actually Sridhar, thanks for asking this question. This is something that's very helpful sometimes when you want to go out of symmetric.
Any more questions?
Something.
If not, let's thank Amrit.
Awesome.